Welcome back. Today we're going to be finishing up the end of chapter 19. Okay, so we've talked about current and how charges flow through conductors. We've talked about resistance and how when the charges flow through, they suffer collisions with the stuff that's there, and along the way, they lose some of that energy. Well, we're going to take a look at what that actual energy loss looks like. And so when we talk about this, when the current passes resistors, it suffers collisions. And so each little charge is going to end up losing some of the kinetic energy it has. Well, the question is, where does that energy go? And it was originally discovered, or in an experiment by James Joule, proved where this energy went. And so what he had was he took, and again, this is not something you want to try at home, but he took a jug of water or a beaker of water, and inside he immersed a resistor. And I'm going to do that. This is our symbol for resistor. We'll talk about that later on. But this is going to be a resistor. So something that will resist the current traveling through. And then he would hook this up to a circuit. So we'd hook it up to a battery. As such, and then coming off the battery, you'd have an ammeter. And that's our symbol for ammeter, but we'll talk about that later on as well. Okay, and then hook it up here. So the current would flow through, and I'll put this in green. The current's going to flow through out of my battery, come down through, go through my resistor, and then come back up and go around like that. And so he was able to determine that how much energy was being lost. Now, real quick reminder that the energy is equal to the voltage times, oops, sorry, hang on. Get rid of this. The voltage times the charge. Well, he had no way of measuring the actual charge. So remember also that the current is equal to the charge divided by time. And so we could actually replace this Q with the current times time. And so, and again, a little manipulation, we'll explain this a little bit later on. But by knowing the voltage across the battery, the current of what was going through and the time that it was on, he was able to predict how much electrical energy was going through that resistor. Well, what he then did was he took, and I'll put this in purple, but he would put a thermometer here. And he was able to show that as you left this on, the temperature of the water would increase. Okay, so this is something you should hopefully, maybe will remember from chemistry, but the amount of thermal energy is equal to the mass of the stuff times the specific heat times the change in temperature. And so what he was able to show is that by measuring, knowing the mass of the water, the specific heat of water, and how much the temperature changed, he's able to show that these two were the exact same. So I'll scroll this up. He found that the energy lost by those charges, I should say charges here, rather than electrons getting back into our conventional current, was exactly equal to what was converted into thermal energy. Again, I showed you that. But again, this proved loco E. Okay? So the electrical energy that was being used by going through the circuit was exactly equal to the thermal energy gained by the water. That was huge. Okay? So we can now write this, and I already showed you the one, that the electrical energy is equal to V times Q, but that's also equal to V times I times T. Okay? But it's also equal to, if we want to rewrite this, and actually, I'm not going to write these out. We're going to address them tomorrow in class. There's a bunch of them in your reference. They will all written out in terms of resistance and current and voltage and time and stuff like that. Okay? But another way that we can look at this, okay, is that this right here, this voltage times the current, is something called power. And we'll talk about that tomorrow in class as well. We'll do investigate. I'll show these to you in a second. But you can talk about your electrical energy as being the power times the time. And this is actually how your electric company will sell you electrical energy. Because what you do, if you ever get a chance to look at your parents' electric bill, your electrical energy is measured in kilowatt hours. So my unit of power and my unit of time. And so it's just another way of describing our electrical energy. And we'll talk about this in detail tomorrow, because it turns out that electrical energy is unbelievably cheap. And we'll talk about how much energy, we'll compare that to the power you had from when you ran up the stairs back in that lab, compared to how much energy it takes and how much it costs. So we'll talk about that a lot tomorrow. We'll do some problems with it. Okay? So this is kind of something we've alluded to. Power, remember, now I'll show you the derivation here. Power, remember, is equal to work divided by time. That's from back in mechanics. Well, we just got done saying that the time, sorry, my fault, hang on one second, that the work done is equal to V times Q. And so we take Q over T. I'll highlight this part. Q times T is actually I. And so remember I told you right up above, the power is equal to voltage times current. This is where that derivation comes from. Okay? And so we'll practice with these tomorrow as well, do a lot of sample problems with them. And so we're going to end there. We're going to do a lot of sample problems with these, talk about how we use this on a day-to-day basis, okay, and how we use it to power our stuff and how that energy conversion affects our lives. So this is the end of chapter 19. Everybody have a great day. We'll see you later. Bye.